Yeah.
Okay. So, good morning, everyone. My name is Dr. Branislav Kisačanin. I teach competitive physics at the Awesome Math Academy, and I will tell you a little bit more about that later on. And first of all, thank you to Brian for inviting me to give a guest lecture at your summer program. I'll be talking about Einstein's miraculous year of 1905, and let's get started. So the agenda for today, for about 30 minutes, I'll be talking about our main topic, Einstein's 1905 discoveries. And then, we can do some Q&A. And I would like to tell you for about 10 minutes about the teaching program that I do at the Awesome Math Academy. And I'll be telling you also about physics competitions. So that's going to be today. So about Einstein's 1905 discoveries, also called Annus Mirabilis, the miraculous year. Let me tell you about Einstein first. He was born in 1879 in Ulm in Germany. He was born on the Pi Day. What a coincidence, right? And unlike what we often hear in the media, he was not bad in math. He never failed math. In fact, he was really good in math. But he used to say that he always needed more math. And I'm sure we all can relate to that when we read some interesting article about some new physics or some new math. We can never know enough math. And I'm sure that's the situation that Einstein also felt. But, looking at his work, you can never think that he didn't know math well. In fact, he learned calculus on his own before he was 15. And he got his doctoral degree in Switzerland in 1905 at the University of Zurich. After that, he became a patent clerk, and that's where he probably was bored and continued his academic interests and discovered some really important things in physics. And for one of those discoveries, he got the Nobel Prize in 1921. But there's more than just one discovery. There were at least 4 great discoveries in that year, and for each of those, he should have received the Nobel Prize, at least in my opinion. After that, he became a professor in Bern, Zurich, Prague, Berlin, and eventually Princeton in the United States. All right. So about these discoveries, okay, in that miraculous year, 1905, Einstein published 4 papers in the top physics journal of the day, Annalen der Physik. That's the journal in German that was really important at the time. And as I said, each of those 4 papers was worthy of a Nobel, at least in my humble opinion. The first paper he published was on Brownian motion, and we'll talk more about what that was. And the second paper was about the photoelectric effect. The third one was special relativity. And the fourth one really described the energy mass equivalence, the famous E equals to mc squared formula. Later, so beyond 1905, he also did some incredible work. He made the theoretical groundwork for lasers. Okay, so probably 30 or 40 years before lasers were really first practically created, Einstein discussed the theory of how the stimulated emission works. In 1916, he published his general relativity, which is still the theory of gravity, even today, after so many years. And also some work in statistical physics, Bose-Einstein statistics, and other things related to quantum physics and unification of the forces in physics. Okay. So let's talk about these discoveries in the context of physics, the state of physics before 1905. How did these discoveries fit into the state of physics at that time? So Brownian motion, you might know that it's really the motion of small particles suspended in water, maybe pollen or some other small particles, moving randomly. If you look at them through a microscope like Brown did, Brown was a Scottish botanist in the 19th century, and when he looked at small particles in water through a microscope, he noticed that they were moving in a very random fashion, and nobody really knew why that was happening. And at the same time, some big names in physics, like Ernst Mach, a big name in physics at that time, they were still questioning the existence of atoms because they couldn't see them, and they claimed, if they're so small as people are saying, we can never see them, and how can we know if they really exist or not? And so what Einstein's theory of Brownian motion did, in which he basically said that the motion of atoms and molecules in the liquid and the collisions of those tiny particles, atoms and molecules, with bigger objects like particles of pollen, these collisions are causing the random zigzag motion of these particles that you look at through the microscope. So Einstein described that thoroughly, mathematically, and the theory explained the observed facts about Brownian motion. And just like with anything in physics, it's not a mathematical proof that really atoms and molecules exist. But when you have a theory that explains so many or all of the observed experimental facts, that's really what counts as proof in science, until you discover some new experimental fact that doesn't fit into the theory. Then you need to look for a better theory. But Einstein's theory of Brownian motion explained all of it, and that was the end of the discussion in terms of science, whether atoms and molecules really exist. With respect to his second paper about the photoelectric effect is an experiment where you shine light on a piece of metal and you observe electrons being kicked out. And nobody could explain how that really worked, and Einstein was able to explain it. And actually for that work he got the Nobel Prize. And the historical context for that is that in 1900 Max Planck was able to explain the emission spectrum of a black body using a strange little trick, saying that energy of light is equal to h nu. H is a constant that we now call Planck's constant. It's a one of those fundamental physics constants. And nu denotes the frequency of the radiation, the frequency of light. That formula, when he inserted it into the existing theory of black body radiation, really solved previously unexplainable facts about the spectrum, and nobody really knew why that thing worked. It was more of a desperate attempt to try different things and see what could explain the radiation spectrum. And indeed, this simple formula, E equals to h nu, worked. It was able to model the spectrum that was experimentally obtained. But nobody really knew what that meant. And while Planck was looking for ways to eliminate this little formula, because nobody knew what it meant, at the same time, Einstein, instead of trying to eliminate it like Planck tried, Einstein embraced it, and he applied the same formula for absorption. Okay, Planck used it for emission of radiation, and Einstein used it for absorption, when the piece of metal absorbs light, and in that process electrons are kicked out, the photoelectric effect. So what Einstein did, he embraced that formula, and we now recognize that as the early days of quantum physics. This formula E equals to h nu is really the basis for quantum physics. It describes the quanta of radiation, the quanta of light, or what we call a photon now. And using that formula and a little bit more math that we are not going to go into right now, Einstein was able to explain how photoelectric effect works. And while you could say that Planck's use of E equals to h nu was the beginning of quantum physics, Planck really didn't intend to do that. And Einstein's use of E equals to h nu for absorption in photoelectric effect is probably a better day to use as the beginning of quantum physics. Number 3 was special relativity. That's really the explanation, or not the explanation, but a better way to look at classical mechanics than Newtonian mechanics, because there were contradictions between Newtonian mechanics and Maxwell's electromagnetism. Newtonian mechanics was considered to be a really beautiful mathematical model of the world. You could write equations, you could design machines. Even today, we still use Newtonian mechanics to design orbits for satellites, or for space probes that go close to Jupiter and Saturn. You don't really need more than Newtonian mechanics for that. There are some rare exceptions. GPS satellites, the satellites that circle the Earth, that allow us to use GPS on our phones, they do require some corrections based on Einstein's discoveries because of the tiny changes in time caused by the motion of satellites. But for the most part, Newtonian mechanics works really well in our everyday life. But looking at it theoretically, there were some contradictions between Newtonian mechanics and Maxwell's electromagnetism. And Einstein was able to reconcile those by introducing what we now call special relativity. And you could summarize the whole thing in saying that instead of Newton's F equals ma, there is a correction. Instead of m in that formula, we need to write m0, which is the mass when the object is at rest, the rest mass, divided by this factor, root of 1 minus v squared over c squared. We call that Lorentzian correction. And so if you do that, Newton's F equals ma becomes more complicated, because now it depends on how fast the object is moving with v, right? And depends on the speed of light, which is the universal, one of those universal physics constants. So Newton's formula becomes more complicated, but this is it. When you use this formula, there are no contradictions between mechanics and electromagnetism. So that's what Einstein discovered. And his fourth important paper from 1905 was a consequence of special relativity. He predicted a formula that really no one expected, something totally new, that energy and mass are equivalent, and there is this equivalence formula, E equals to mc squared. And we know it's true in practical terms too, because power stations based on nuclear energy, so nuclear power stations, use this formula every day, because when uranium and plutonium atoms, when they undergo radioactive splits, the so-called fission, in that process, a tiny bit of matter, tiny bit of mass is converted into energy, and then that energy heats up the water around the reactor, that goes into turbines, and we produce electrical energy using that. And also nuclear explosions are based on that very same formula. About, I believe it was about half of a gram of matter was converted into energy in the Hiroshima atomic bomb explosion. Half a gram of matter converted into energy caused all that terrible destruction. And of course, fusion that's happening inside of the sun, where atoms or nuclei of hydrogen, so pretty much protons, merge together to form bigger particles, alpha particles, the nuclei of helium, basically. So you can say that hydrogen is being turned into helium in a way during this nuclear process called fusion. And in that process, a small part of the mass of the original hydrogen nuclei of protons in that process is being turned into energy and radiated, and that's all the energy that sun is emitting and giving basically life to Earth, right? Okay, so that's in a nutshell about those big discoveries that Einstein made in 1905. And I don't know if there's a way for you guys to ask me questions. I'm not used to Meet Google. Is there a chat box, or is there a good way for questions?
Oh, there's a chat box on the side and on Google Meets. Okay,
let me see if I can find it. If I can't find it, you will read it to me, okay? If there are any questions.
Yeah.
Okay, I do see chat. Okay. What kind of math did Einstein use to derive these formulas? Interesting question. So calculus is definitely a very useful tool. So to understand, to be able to read Einstein's original papers, you do need to know calculus. Also, for Brownian motion, he used statistics. So it is very useful to know statistics, the meaning of various expected values and means and all of that. So definitely calculus is an important prerequisite to read Einstein's papers. And you have to be aware that these are research papers, and even if you really know calculus well, it's still not going to be easy to read the original papers. But if you read about that in a textbook, that's going to be explained much better. Okay, when Einstein wrote those papers, he relied on some earlier papers, and he's not explaining everything he's doing, but he's referencing previous research papers. So it's easier to read about that stuff from a textbook than from the original papers. Okay, another question: what is the difference between special and general relativity? Another really good question. So the two names are maybe deceptive. You might think that there is a lot of connection between the two. There isn't a lot of connection, okay? Special relativity talks about the effects that happen when objects move really fast, meaning close to the speed of light. And there are several very strange things that happen in that realm of science. As you get closer to the speed of light, the mass of objects really dramatically increases. And if you were somehow able to get really, really close to the speed of light, let's say 99.99% of the speed of light, the mass of the object would increase hugely. Okay. Another thing that happens, the length of the object in the direction of motion becomes shorter and shorter. Okay, the objects become smaller and smaller in that dimension. And also, if you have a clock, as you travel at a huge speed, close to the speed of light, even though you would think that nothing strange is happening with time, if you compare your time in the super fast spaceship, it becomes much slower than for somebody who stayed on the Earth. Okay, so very strange things happen when objects travel really, really fast. In terms of general relativity, it really deals with gravity. When Newton wrote his famous formula for the force of gravity, which is capital G, the universal gravitational constant, times one mass times the other mass divided by the square of their distance, he acknowledged that he didn't know how gravity really works. But his formula for the force was really super duper correct. But even the great Newton didn't know how gravity really works. And in fact, he thought that its action is instantaneous, meaning that if the sun somehow disappeared momentarily, okay, for 10 seconds, let's say, that we would feel for those 10 seconds, we would immediately feel lack of sun's pull, which is not true. Now we know that it takes time for gravitational effects to spread around the space. And that's what these recent experiments, LIGO experiments, measuring gravitational waves, that's what they really do. They measure the effects of, let's say, two black holes circling one another or maybe colliding, and all that can be felt with this time delay because gravity has a finite speed of spreading around. So general relativity really talks about how gravity works. And what Einstein did, he used some really fancy math, talking again about which kind of math he used. Riemann's geometry describes the space, allowing it to be curved, not like what we imagine, what we call Euclidean space, that everything is straight and simple, Riemann's geometry allows the space to be curved, and that's exactly what Einstein used. And he figured out that what happens around big masses like the sun or even the earth, I mean around any mass, but it's especially noticeable around big masses, the space becomes curved, and that causes objects to kind of tend to go in that direction. Even light traveling near sun's surface gets bent, and the light doesn't travel in a straight line anymore. And we see that in astronomy, so-called gravitational lenses. A distant galaxy will act as a gravitational lens for objects behind it. So, in some places, Hubble telescope pictures really show these lens effects caused by huge galaxies that lie between us and this really far away object that's being lensed. Okay, so in very few words, special theory of relativity talks about what happens to objects when they travel with high speed, close to the speed of light. And general relativity is the theory of gravity. Okay, let's look at the next question. Why does the general relativity paper not be included in the, well, it became, it was published later. General relativity was published in 1916. So after Einstein made these amazing discoveries in 1905, he worked on the theory of gravity for a number of years, about 10 years, and he published the first major discovery about that in 1916. Is it now a very fundamental for astrophysics and some other field? Yes, it is. It is. It is the current theory of gravity. That's how we understand gravity today. Okay, another question is because it was, okay, thank you for that answer. Okay, is there a more accessible approach to the mass energy equivalence formula without relying on Lagrangian Hamiltonian formalism? I don't know. I don't know. I wouldn't speculate on how to derive E equals to mc squared in a different way. So I don't know. Sorry. Could you give some more detail on what contradictions were between Maxwell's electromagnetism and Newton's mechanics? I think I'll skip on that. It would take me a little bit too long to explain, but I would recommend looking at your local library or maybe getting it on Amazon. These books are probably not more than $10. Einstein himself wrote a really nice, popular account of special relativity, and there are other really nice books that explain that. So yeah, I'm gonna skip on that. It would be a little bit too long to explain here. Okay. How much tensor calculus or tensor analysis is required in general relativity? Yes, the math behind Riemann's geometry is tensors, and description of what happens in it definitely involves tensor calculus. Yes, so it is, for general relativity, tensor calculus is necessary. In terms of special relativity, no, because special relativity doesn't deal with curvature of space and so on. So you don't need tensors for that. Okay, I think we answered some really nice questions here, and I apologize we didn't answer two of them because one of them I don't know, the other is a little bit too involved. Keep asking questions. I'll look again a little bit later. Let me now see, where were we? Okay, so yeah, and one of the points I wanted to make is, so this was year 1905. The state of physics was really in a big flux. So many changes were needed, and Einstein did many of these necessary changes. Okay, and what's interesting, that year Einstein turned 26. So very young, very young. All right. I wanted also to say a few things about this formula that gives the corrected value for the mass of objects, because it depends on the speed of the object. Okay, what happens when v, the velocity of the object, is much smaller than the speed of light? Well, let's see. If v is much smaller than c, then you can pretty much neglect this term, and especially because it's squared. So if v is much smaller than c, v squared is even smaller, relatively speaking, than c squared. So really, in our everyday life, when our speeds, when we travel, even when we travel by airplane, our speed is so much smaller than the speed of light that you can say that this is practically zero. And then, of course, 1 minus 0 is 1, root of 1 is 1, and you get that m is m0, the rest mass. And that's why nobody really noticed that something was wrong with Newton's mechanics, with F equals ma and everything else, because these things become observable only when the speed of the object is, let's say, I don't know, 50% of the speed of light, or maybe 10% of the speed of light. Below that, these effects are pretty much negligible. Okay, and the reason I'm going in this direction, talking about this asymptotic analysis or these approximations, is because that is one of the things that we do in my classes. And let me show you one of the slides talking about common approximations used in physics. Frequently, when you write an equation that describes something, for example, a pendulum, your differential equation will involve sine of x. And if you try to solve it with sine of x in that equation, things become very complicated. But you can say that for small values of x, and x must be in radians for this to work, not degrees, when x is in radians and x is much smaller than 1, typically, let's say, less than 0.1 or something like that. Depends on how much accuracy you want to accomplish. But for small values of x, and in the case of a pendulum, the small oscillations in the pendulum are probably things less than 10 degrees to one side, 10 degrees to the other side. You can approximate sine of x with just x. And then your differential equation becomes much simpler. It becomes a linear differential equation. It can be nicely solved, and you can get a nice formula for the period of the pendulum, of the ideal pendulum. It's 2 pi root of L. L is the length of the pendulum divided by g, the gravitational acceleration. Okay. Other useful approximations that we see in physics, instead of e to the power x when x is small, we can write 1 plus x. And of course, if you need more terms, you can continue with Taylor's expansion or Maclaurin's expansion, that is around 0, so it's the same thing, Taylor and Maclaurin. 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. But frequently it's sufficient to use this linear approximation, first order approximation. E to the power x is 1 plus x. We can also apply similar reasoning to this binomial, instead of the binomial formula, full binomial formula that Newton derived, we can approximate this just by the first order approximation. So 1 plus x to the power a is 1 plus ax. And this particular approximation, this one, can be applied to our previous formula for the mass right here. A in this case, because this is the reciprocal of a root, a in that case is negative 1/2. So we would have that a is negative 1/2. So 1 plus x to that power, it would be 1 minus x over 2. And x in our case would be v squared over c squared, right? So you can say that this formula can be approximated by using this formula. Okay, and you would get the same conclusion that when v is very small, we basically get that the two masses are equal, the rest mass and the actual mass. Okay, and some other formulas that we use in physics, a to the power x can be approximated with 1 plus x ln a. That's really the generalization of this formula here, e to the power x. Okay, when a is equal to e, ln a is just 1, so you get the same formula. This one and this one, they're consequences of the second formula. So 1 over 1 plus x is roughly 1 minus x, and the root of 1 plus x is roughly 1 plus x over 2. And the reciprocal of that we just talked about would be 1 minus x over 2. Okay, and so as I mentioned, this one we use in derivation of the ideal pendulum formula, the period for that. And then if you want to see how the period of the pendulum changes with changes in L, the length of the pendulum, that's called the sensitivity analysis. You can use this approximation here to see that the rate of change, delta t over delta L, is really t over 2L, something that we also need sometimes in our physics problems. Okay, so yeah, that's a little hint of what kinds of things we talk about in our physics, competitive physics classes at the Awesome Math. We really expect our students to come in with strong math abilities, and that allows us to go really fast through physics and allows us to give a serious jump start to our students in terms of physics competitions. So let me say a few words about our classes. The website for the Awesome Math Academy is this here, and many of you will probably know that Awesome Math has summer programs, which are strictly competitive math classes. And we also have the Academy, Awesome Math Academy. These are the programs during the school year. And there we have math classes, we have physics classes, and we have chemistry. And in terms of physics, our competitive physics is targeted primarily at F equals MA. That's the first level of competitions in physics. But our students tell us that what they learn with us is useful to do credit by exam if they want to skip a class in their school, and also useful for AP, because our classes really focus on problem solving way beyond AP classes. So what you learn in our classes really allows you to master AP much better. Okay, our classes are semester courses. I'm talking about physics. Each class has 11 units or 11 weeks in a semester. Level 1, you don't need to have any prior knowledge of physics, but we do expect strong math at the Algebra 2 level. And when students finish level 1, they're ready to do more than 1/4 of F equals MA, which is not enough to go to the next level, but is a serious thing because F equals MA competitions are pretty difficult. So you're ready to make a serious dent in doing those problems. Level 2, that's really meant to prepare you to pass F equals MA. And we expect prior physics knowledge, maybe even AP Physics B, strong math at the pre-calculus level. That's because F equals MA does not use calculus at all. And after level 2, students will be ready to do more than 1/2 of F equals MA, which is about enough to pass to the next level. You do need to do some more preparations. You need to invest more time than our class, but our class gives you a serious jump start to be ready to pass the F equals MA and go to the US Physics Olympiad. We now have level 3 as well. We expect you to already be very strong in physics and to know basic calculus because US Physics Olympiad uses calculus. And while F equals MA competition is only mechanics, classical mechanics, US Physics Olympiad is all of physics. So it goes deeper and it goes broader. Okay, and we have level 3 for that. So a little bit of advertising. Fall and spring registration is now open on the website. And just a reminder, we also offer math and chemistry. Okay, let me tell you a little bit about myself. So again, my name is Dr. Branislav Kisačanin. I have an academically crazy family. My daughter, Milena, is a Deadman Scholar. They call that the Rhodes of Texas at the University of Texas. My son, Nikola, went to ISEF, the International Science Fair, when he was in 9th grade. And my wife, Alex, teaches innovation. And actually, she now teaches chemistry at the Awesome Math Academy. Okay, I have a PhD in computer science. I work in computer vision, artificial intelligence, self-driving cars. I used to work for Delphi, Texas Instruments, Interface, and now I'm with NVIDIA, a really great company when it comes to artificial intelligence, and of course, computer games hardware. I'm a passionate teacher of gifted kids. I started with Dr. Andrescu, Titu Andrescu, at Metroplex Math Circle at UT Dallas. And then I joined his summer camps, teaching. Basically, I didn't update this list, but I taught all level 1 classes. So these 3 and combinatorics 1. And now I have taught combinatorics 2 this summer. So I've been teaching quite a bit during summer classes. And at the Awesome Math Academy, I've been with the Academy since it begun a few years ago with math talks, and then I created all 3 physics courses, and I teach all of them. Okay, so yeah, that's about me and what I like to do. And now let's focus on F equals MA. And as I said, F equals MA is classical mechanics only, no calculus. And if you compare it to mathematical competitions, AMC is the first level, AME is the second level, and so on. In physics, judging by the difficulty of problems, F equals MA is really more like AME. There is no competition in this sequence that would be corresponding to AMC competitions in terms of difficulty. So F equals MA is the first level, but it's already very hard. Okay, about 1/4 of the problems I would consider to be easy, and that's where we focus with our level 1 class. About 1/2 of the problems are hard, And that's where we focus with level 2. So when I said that students who finish level 2 can do more than 1/2 of F equals MA, I really meant 1/4 plus 1/2. So maybe I should make that number bigger in that slide. And then the last quarter of the problems at the competition are very hard problems. And my advice usually is to be able to, to try to recognize those very hard problems and not even try to do them, okay? If you are already experienced with physics competitions, maybe you can do those very hard problems, but really they don't matter much if your goal is to go to the next level, okay? Because you can get to the next level even without any of those very hard problems. It becomes difficult to recognize them, okay? It's not always easy to recognize which problem just sounds hard, but is very easy. And there are such problems, and we talk about that in my class. With experience, you will be able to recognize those very hard problems and avoid spending time on them. And that's because all problems carry exactly 1 point, regardless of the difficulty. Easy, hard, or very hard, they all carry exactly 1 point. And how many points do you need to pass? It's usually between 1/2 and 2/3 of 25 problems. It usually aligns really well, if you identify all easy and all, let's call them medium hard problems. Usually if you do those, so level 2 type knowledge, level 2 class type knowledge, you will definitely be higher than the threshold, okay? And there are some specific things to the rules, okay? And so we'll look at that in the next page. In particular, whether it's okay to be guessing in your solutions, are there negative points for guessing, and whether a calculator is allowed. These things occasionally change between years, not very often, but if they do change, it's important to be aware of that change. So this is from 2017. And the rules are still the same. Of course, we don't know what's going to happen in 2021. Maybe they will change the rules, but in 2020, the rules were basically identical to this. So there are 25 questions, and you only have 75 minutes to do them. And again, since each question is just 1 point, it's better to focus on easier questions. Interestingly, they want you to use G equals to 10 newtons per kilogram. The correct value is 9.8 or 9.81, but they want you to use this. I guess they want to allow people to do mental calculations if somebody forgot a calculator, okay? You need to select a single answer that's the best response to a question. This really means in cases when the correct answer is, let's say, 1.2, but in their answer choices, they offer, instead of 1.2, they offer, let's say, 1, 10, 100, and so on. The closest answer will be 1, even though the true answer is 1.2. So they want you to choose the one that's closest. And 1 point for each correct answer, regardless of difficulty. And since I think 2015, they did not apply any penalties for incorrect answers. They allow a handheld calculator. If you bring some kind of big graphics calculator and all that, you will be asked to reset it to clear its memory. And again, all questions are equally weighted, but not necessarily the same level of difficulty. And that's basically it. The rest of the rules are nothing terribly surprising, but this is important to know if you're going into that competition. And then let me talk a little bit about the logistics of taking F equals MA competitions. It's the best if you can take that competition in your school, but many schools do not even know these competitions exist. So it's a good idea, if you want to participate, at the beginning of the school year, talk to your physics teacher and check if they organize F equals MA contest in the school. If they don't get mad. It's not uncommon. Many teachers don't really know about the competition. So tell them about why it's an important competition. Tell them it leads to the US Physics Olympiad and eventually to the International Physics Olympiad, that it's really good for you and for the school to participate in that. If that doesn't work, if you're not able to convince the school to organize it, there are alternatives. Figure out in your local homeschooling community. They will often organize it. Ask at a local college or university. They often have outreach programs where they organize things like this. And if even that fails, you can always find a retired teacher or a librarian who will want to help you organize the contest, even if it's just for you. That's why it cannot be your parents. Your parents can help you find a retired teacher or a librarian, but your parents cannot organize it, right? Conflict of interest. Keep in mind that the registration deadline is usually in early December. So, you know, give it some time to figure out if your school is organizing it. Give it some time to find a librarian or a retired teacher or somebody who will do it for you as a proctor. And the tests are around January 23rd, 31st, something like that. And it's okay to take both instances of the test, A and B. You don't have to, but you can take both. It's okay to take both. How to prepare? Well, this webinar, well, it really refers to a previous webinar I held elsewhere. So listening to these webinars on competition, you can find a recorded webinar I'm referring to here on YouTube. Just search for Physics Awesome Math Academy and you'll find it on YouTube. So that's a good start. You need to be really dedicated. So a lot of self-study. And our online physics classes can certainly be a big help, give you a big jump start towards successful physics competitions. We have great materials that you really cannot find in any books. That's because F equals MA are no calculus problems, but hard. So hard physics problems without calculus. It's just not easy to find materials like that. If you go to college textbooks, there will be really nice problems, but many of them will include calculus, and that's not something you need for F equals MA. So we have developed really great materials to prepare for competitions. We provide strong guidance. We have really great teaching assistants. When you submit your homework, they will do a lot of detective work to figure out if you made a mistake, where it happened, to really pinpoint and tell you this is where you made the wrong turn. That really helps. That kind of detailed feedback really helps with fast-paced learning. And you know, if you need more information, you can go to our website, theawesomemath.org, and find more information there, or send us an email. We'll be happy to tell you more about our classes. Recently, I wrote a book with solutions, detailed solutions of previous 10 years of F equals MA problems. I wrote that book with my most successful physics student, Eric Zhang, who won 3 golds at US Physics Olympiad. He was also invited to be on the team for the International Physics Olympiad, but he declined because he was already on the team for International Olympiad on Informatics, and he got 2 golds there at the international level. So really brilliant student. And he and I wrote this book that is now a free download at AAPT. AAPT is the Physics Teachers Association that organizes F=MA competitions and the team for the International Physics Olympiad. So we wrote that book and we gave it for free to AAPT to put it on their website so everybody can download it. And the link is right here. You don't need to copy that link. You can simply Google it, and you will find it on their website. Okay, so I think that's pretty much it in terms of what I had for you today. I have another slide, but that would probably take another 10 minutes to show you the difference. When AAPT posts solutions to competition problems, it's usually very short. That's why I say, really, that's your solution? And then if you look at our book, you will see a much more detailed explanation and solution, okay? And this is one of those really hard problems that you probably don't want to be solving in the competition, but it is a good idea to understand what's happening there and what physics and what math is behind it. And in particular, in this problem, we use quite a bit those approximation formulas that we talked about earlier. Where is that now? Okay, this stuff here. All right, so let me see if there are any questions. Thank you very much for letting me talk to you today. And let's see if there are any questions. So let's see. Okay, do you think we still have the F=MA this year? Whether it will be pushed back? Yeah, F=MA actually happened in early January. That was before COVID, but the US Physics Olympiad did not happen, and I don't think it will be happening. Of course, nobody knows what's happening in the spring with respect to the virus and all that. Hopefully they'll make things online. I really hope so. So we'll see. Out of curiosity, is there a physics camp like there is MOP? So there is. All people who are invited to the team, to the International Physics Olympiad team, they could go to this camp, and then the final team is picked from among those people who were at the camp. Okay, thank you for a great lecture. Oh, my pleasure. Thank you for acknowledging it. Okay, Brian, back to you, and thank you again for inviting me.
All right, thank you so much, for coming. Let's give Dr. Kisačanin a round of applause.
Okay. That's nice. Thank you very much.
All right. Thank you.
Okay. Have a great day. Bye-bye.